Thank you. The second part of this seminar inspects the human predicament using nonlinearity. Let me suggest that the human predicament is pretty simple. There's not enough stuff to fulfill everyone's needs. People get into fights, physical or economic, to see who gets the stuff and who goes without. And the loser dies or fights back harder, making conflict. Higher gas prices, higher food prices relative to the value of labor means more conflict. Terrorism in failed states means more conflict. Overuse of renewable resources like forests or fisheries. Depletion of fossil fuel supplies like petroleum and deep aquifers. Lowering of water table through irrigation. And filling of waste sinks makes supporting resources more scarce, and thus it increases conflict. While most people think there is rising conflict, they don't think that civilization will collapse. They think that generosity will contain conflict. They think compassion will reduce it. They think recycling and conservation will reduce scarcity, and this will contain conflict. They believe technology will provide the extra goods and services to prevent scarcity and thus limit conflict. And finally, if there is a war or deprivation, they believe we can muddle through. What if I can show you that we have as much chance of muddling through increasing conflict as we have of reducing a child's injury if we put our arms out to hold them back? What if I can show you that something like an accident is in our future? We don't see it. When we finally see it, the available behaviors to address it will be analogous to trying to buckle a seatbelt while careening toward the dashboard. And after the accident, civilization will be so broken, there will be little chance to repair it. Why? Because conflict in our system is nonlinear. Because of this nonlinearity, we highly underestimate what we face, and we overestimate our ability to address it. This is a lot different than most people think. So let me ease you into this new view by reminding you of the advice Pogo provided. The future ain't like it used to be. 70 years people experienced meteoric rise in well-being. To name a few: flush toilets, electric lights, phones, automobiles, antibiotics, jet planes, integrated circuit, plastic, money, bionic parts, and the internet. The middle class has seen a century of impressive improvements, and they are looking forward to some impressive new ones. Cyborg implants to replace worn-out ears, genetic modifications that undo wayward gene expressions like Tay-Sachs, cancer, and sickle cell anemia, and nanorobots that will do everything from repair nerves to clean out arteries. The important question is, can we keep these improvements going? Why not, the optimists say? We've done it in the past. If we maintain the infrastructure, apply our capital to new technological projects, we should be able to produce the required goods and services to even a growing community. Optimists believe the disruptions and social conflict that arise from intermittent scarcity have not crippled the advancement of technology. On the contrary, conflict spurs technological advancement. Has anything changed? Is there any reason for these optimistic arguments to grow weaker, while more pessimistic arguments grow stronger? Yep, today is different. We can no longer easily migrate great distances, overwhelm less developed locals, and take their resources. Oil production is peaking. New customers of oil, like China, drive up demand and price, not production. Today, the Earth's air, water, and oceans can no longer absorb our waste without lowering production. And one more thing has changed, something we seem to universally overlook, something that might be most important to our future. The personal footprints of 6 billion people overlap more each day. We are more uncomfortable with each other's presence, and this expands social conflict at every level. All of these changes exist because what we thought was unconstrained growth is actually constrained growth. So our next task is to get a better understanding of the difference. First, let me describe unconstrained growth. You probably know most of what I'm about to say, but the devil is in the details, so I will repeat for clarity. Think of a dish with one cell in it. A microscopic view of that cell is in this small circle. Every day the cells divide. Each successive day they will be twice as many cells as the day before. After 1 day there will be 2 cells. After 2 days there will be 4 cells. After 3 days there will be 8 cells. Who can tell me how many cells will be in the petri dish on the 10th day? Well, my question's rhetorical, I know you know. Let's keep our focus on how nonlinearity does not shape our behavior. The answer is about 1,000. After 20 days it'll be about 1,000,000. After 30 days it'll be about 1,000,000,000. Let's plot the data. The y-axis goes 0 to 1,000,000,000, and the x-axis goes 0 to 30 days. After 1 day, there will be 2 cells. After 2 days, 4 cells. After 3 days, 8 cells. After 10 days, the population is 1,000. And after 20 days, the population will be about 1,000,000. Even 1,000,000 is only 1/1000th of a billion. After 30 days, the population is 1,000,000,000. Let me throw in a few more points, and it looks like a normal, unconstrained, exponential growth curve. Growth will continue like this as long as space or nutrients provide no constraints. For example, after 40 days, the number of bacteria will top 1,000,000,000,000. You probably got a feel for unconstrained biological growth. Now, I would like to introduce the concept of constrained growth. As a first step, let me use a French riddle called the lily pond problem. 1 day you plant a lily in the pond. The lily doubles in size each day. On the 30th day, the pond is completely full with lilies. On what day did the lilies cover half the pond? You probably know the answer from Ecology 101, the section on exponential growth. The answer is the 29th day. The lily pond problem is a concocted learning environment. While it makes for an alarming awakening of the meaning of unconstrained exponential growth, and the graph shows the pond half full on the 29th day, there is a difference between unconstrained growth, depicted by the red dots, and another curve, the constrained growth curve, which will do a better job of connecting human procreative behavior to social conflict. Let me develop this second curve. Every lily pad that gets food and energy from the sun has a similar propensity to multiply as shown by the green arrows. However, common sense tells us that 2 lilies next to one another inhibit each other's growth. So cluster constraints, denoted by the red arrows, slow growth, not only of the surrounding lilies, but also partially surrounding lilies. Also, as the cluster expands toward the pond's edge, the boundary constraints shown as red arrows begin inhibiting growth. When there is only 1 lily in the pond, there are no cluster forces, no cluster constraint forces, and only the smallest constraint from the pond's edge. However, with the creation of the second plant, both kinds of constraints begin increasing. It is obvious that the 1,000 lilies that exist at 10 days create a lot more cluster constraints than do the 8 lilies on the 3rd day. In spite of the increasing constraints, the curve still rises rapidly. In fact, the population expands more on each successive day. That is, the number of pads added on day B exceeds the number added the day before, day A. While the cluster constraints do not appear to slow total growth, they do increase the time needed to double the population. That is, in the beginning, the lilies double their population each day. But as the cluster constraint forces grow, the time needed to double increases. It increases relative to the constraint growth curve. Each point on the Relative to the unconstrained growth curve, each point on the constrained growth curve moves to the right. This increase in doubling time continues until the pond is half full. Then something striking becomes apparent. The population can only double once more. 100 days later, the lilies will still not have completed the next doubling. If the plant's energy to reproduce remains constant, if the birth rate remains constant, how can the population growth slow down? The death rate increases. The constraints have been increasing the death rate since the first lily doubled. The death rate increases until the pond is full, after which time a weaker lily has to die to let a new lily live. The facts produce a curve during the last doubling that is a mirror image of the red dots during the first 29 days. So instead of doing the calculus, I will do what kids do when they don't want to type. They cut and paste. So the first thing I'm going to do is make a copy of the original curve. And then I'm going to move it over to the right, and then flip it, the right side over to the left, and then flip the top to the bottom, and then let's move the curve up to the left. Aren't computers fun? I just avoided having to explain the solution to this nasty partial differential equation. Let's look at what the constrained growth curve tells us. You already know the top half of the curve describes the last possible doubling. However, there is more to learn, which ties human procreative behavior to our coming conflict. What comes next is the most important part of this talk. You are about to learn about What comes next is the most important part of the talk. You're about to learn about the crash dynamics of growth within constraints. Now focus on the forces that create this curve shape. Constraint forces begin their counterforce to population growth with the first lily, and as the population rises, the force gets bigger and bigger and bigger and bigger and bigger and bigger until the constraint force is so large the population almost stops increasing. Look at the size of the arrows and look at how they grow larger. Very slowly for most of the curve, then rapidly as the curve approaches the pond's limit, and finally the constraint forces increase nonlinearly. The same as automobile stopping forces that increase nonlinearly as the stopping distance approaches zero. Just as an understanding of exponential growth explains how a flat curve turns into a steeply rising one, an understanding of the rapidly increasing constraint forces explains how this rapid growth ends so quickly. The end of population growth in the lily pond looks pretty placid. The pond, without a sound, went through the transition from exponential population growth to a family of lilies just replacing their dead. And now you know the difference between unconstrained growth and constrained growth. Constrained growth stops growing. For lilies, this is quite beautiful. So what does this constrained growth curve and these constraint forces, which describe lilies in a pond, have to do with the human conflict? Humans are not lilies. Their transition from growth to constant population will not be placid. Human consciousness includes a quantitative view of the past, plans, goals, and expectations for the future, capacity to upgrade their technology, and create and store supporting resources. And as a result, they can consume above subsistence. This means Lily's consumptive behavior is required for subsistence. Human consumptive behavior above subsistence is elective, and this election is almost unlimited. Imagine the consumptive behavior of pharaohs making pyramids. Lilies obtain their resources from the environment and have no consciousness of their competitors. Humans acquire resources from both the environment and interactions with other humans. For humans, as long as the environment supplies an unlimited amount of resource, for example, air to breathe, the green box, the requirements of two humans for air does not bring them into competition with one another. Thus, the air resource provides few opportunities to generate conflict. But when a resource is limited, like the nutrients in a pond, and competitor A or competitor B requires all the resources to survive, competition determines who gets the resource. With lilies living at subsistence, any loss of nutrients in competition means death. Lily A does not know that it killed Lily B, and Lily B attempts no retribution on Lily A. But for humans, living far above subsistence, both eat and sell nutrients, who both eat and sell nutrients obtained from the pond. Loss of pond resources to A in competition means B's loss of well-being, not B's death. Loss of well-being leads to social conflict. Now, let's combine this view of human use of resources, loss of well-being, social conflict with the constrained growth curve. The vertical axis of this graph has been changed from population to the collection of all individual footprints on Earth. The horizontal limit line is now global carrying capacity. Actually, it's not horizontal, it slopes upward today and could be sloped downward tomorrow if we run out of oil without finding a suitable replacement. In this region of the curve, when global footprint values are far from carrying capacity, resources supporting human life are much like the air we breathe. The market price of these resources is capped by the cost of accessing unused sources. However, when global human footprint approaches the carrying capacity, for example, limits of a fishery, the ever expansion of fish delivery slows. In the time period where the curve goes from steep to near flat, rich consumers bid up the price of fish, and those living at their financial limits lose access to fish that they previously could afford. Their well-being decreases. And with enough depression in a range of human needs, social conflict increases. Throughout history, humans managed the social conflict resulting from scarce resources and loss of well-being. They killed or enslaved competitors. They creatively imposed treaties, laws, and moral codes. They invested in infrastructure and technology with expectations that it would prime the economic pump, and they developed various schemes of wealth redistribution, more recently called social safety nets. Given the rising well-being of even losers of the last century's conflicts, humans have developed a confidence in these mechanisms to limit social conflict. However, using these experiences to predict how well they will manage social conflict in the future, maybe like using the braking experiences in the blue part of the curve to predict what will happen in the red. Remember how our experience underestimated the danger we were exposed to? What if our ability to predict the success of our social conflict controls is based on our experience and social conflict grows nonlinearly? Then our predictions of their success based on linear extrapolation will underestimate the magnitude and onset rate of coming conflicts and overestimate our ability to manage them. Let me use 4 curves to describe in another way our blindness to this coming crisis of conflict. This purple line shows the rise of the average individual's consumption or footprint over time. The bottom of this curve lies along an individual's subsistence consumption. And below this line, people die from insufficient water, food, or shelter. This is the point where hunter and gatherers change to farmers. Before this point, each human consumed what he or she needed to survive each day. And after this point, an individual's daily consumption could be any amount. The present is this vertical line. Today, the average human footprint is far above subsistence. Now, let me add a second familiar curve, the constrained population growth curve, the one with 8 kids per family and high death rates due to poor healthcare, starvation, and deadly conflict. The one that has reached 6.7 billion people. It's a good thing we had constrained growth. With unconstrained growth, if each woman who lived at the time of Christ had only 3 children, not 8, each of whom lived to the age of 60, then the 6.7 billion mark would have been reached 300 years later. The only reason it took 1,700 more years is a huge death rate. The third curve, a green line, is the global carrying capacity. It is not just space per person, but also heat, transport, recreation, and entertainment. The units of this curve are footprint units. The zero reference for the green carrying capacity line is here, and the carrying capacity curve is sloped upward as time increases to reflect humankind's creative genius. The fourth curve, a blue curve, is the total human footprint curve. It is created by multiplying the per capita consumption at a point in time times the number of people at that time to get a total human footprint at that time. Since the units of the total human footprint curve are the same as the units of the green carrying capacity curve, and since both curves have the same zero on this graph, the point where they intersect is of interest. Remember the lily pads crashing into each other and crashing into the sides of the pond during the last doubling? Well, for humans, as the blue curve approaches the green curve, as the total of all human footprint collected together approach the carrying capacity, the collisions among these individuals increase. The needs of one person for the resources or services currently used by another increases. And as the constrained forces driving these footprint collisions increase nonlinearly to enormous values, so does social conflict. Somewhere near here, the resulting expanding social conflict will hit us like an unexpected car crash. We will know that civilization is broken when half the population of the world, after experiencing enough loss in their well-being, all turn into radical nationalists and come after anyone who has taken or appears to be taking their well-being. One can only conclude that the human community's biggest and possibly its most hidden problem is an imminent crisis of expanding conflict. You all know, before you all knew, there was an elephant in the room. There was an overpopulation problem. You all knew the elephant was creating environmental problems and some social conflict. But now you know the elephant can abruptly wake up and he can start crashing around in the room and breaking and trampling. The elephant has the power to collapse civilization and maybe even end the human experiment. And you know a few more things. Limiting global warming, or managing peak oil, or resolving scarce water will not keep the elephant from collapsing civilization and turning your child or grandchild into something like a Somali war orphan. Protecting them will take more powerful acts. Let me suggest a trend that can address the elephant problem. Rapid population decline. Not created by death or disease or genocide, but by limiting each parent to fathering or mothering one child. Before you tell me obtaining these behaviors are impossible or immoral, let me show you what happens to the four-curve graph if one-child behaviors were universally adopted. First, per capita footprint will continue to increase. Next, implement the one-child limit. Voila, the population curve will decrease by half every generation. Now, when we multiply any point on the rising per capita footprint curve times any point on the falling population curve, you get a point on the total human footprint curve. Oh my God. A point that drops away from the global carrying capacity curve. This means the constraint forces drop. This means the forces pushing one person into another are falling nonlinearly. This means conflict must be dropping and peace must be increasing. The one-child limit, resulting in rapidly decreasing population, appears to be a way for humans to have ever-increasing well-being and ever-increasing peace. Again, implementing rapid population decline seems impossible. Getting everyone to have only one child is beyond our imagination. But everything does not have to remain beyond our imagination. In this seminar, you found out that overpopulation is a bigger problem than you ever imagined. You learned that your child was at a much greater risk. Let me leave you with this final thought. Have you learned enough to motivate you to start work on solving the impossible?